The instrument panel, or dash. It is the driver's information center on today's AMC cars and Jeep vehicles. Each driver looks at the instrument panel differently, yet all drivers must rely on the instrument panel for vital information on what's happening under the hood. Is the battery charging or discharging? Is the fuel tank full or almost empty? Is the oil pressure high or dangerously low? Is the engine temperature okay or dangerously high? Knowing the answers to these 4 questions can help the driver avoid some frustrating experiences as well as expensive repairs. The engine information is given to the driver by dash gauges or indicators, and this release, the 4th in our continuing series of basic electrical training programs, will cover what you need to know about dash gauges and indicators. You will use 2 training tools. This film is one, and a film reference book is the other. Each carries a different message to help you become skilled on dash gauges and indicators. In this training film, you should learn about the various types of indicating devices used on AMC cars and Jeep vehicles, and you should gain an understanding of the operation of each indicator lamp and dash gauge. In the film reference book, you can refer to diagnostic charts and service procedures for gauges and indicators used on the different models of AMC cars and Jeep vehicles. First, let's look at the various types of indicating devices used to tell the driver about charging system operation, fuel supply, oil pressure, and engine temperature. There are 2 basic groups of devices, indicator lamps and gauges. The indicator lamps are normally off and are lighted only when a problem occurs. The gauges do much more. They continuously monitor the engine conditions. For information on charging system operation, an indicator lamp, an ammeter, or a voltmeter may be used. The indicator lamp lights if the alternator fails to charge the battery. The ammeter indicates charging or discharging, and the voltmeter indicates the charging voltage. For information on the fuel supply, a gauge is always used. It indicates the fuel level in the fuel tank of the vehicle. It does not indicate gallons of fuel or the rate of use. For information on the oil pressure in the engine's lubricating system, an indicator lamp or a gauge may be used. The indicator lamp lights if the oil pressure drops dangerously low. The gauge indicates the actual oil pressures in the system. Neither device indicates the amount of oil. You have the same choice of indicators for information on the temperature in the engine's cooling system. An indicator lamp or a gauge may be used. The indicator lamp lights if the coolant temperature climbs dangerously high. The gauge indicates coolant temperatures ranging from cold to hot. Neither device indicates the amount of coolant. It's easy to understand the operation of these various dash gauges and indicators. All are electrically operated, and all have a sending unit which monitors the engine condition, a recording unit which displays the information on the instrument panel, and of course the wiring in between which carries the message. The indicator lamps, or warning lights, as they are often called, are simple on-off devices. So let's learn how they work first. Here's how a driver sees the charge indicator lamp. When the ignition switch is turned on and the engine is not running, the lamp lights for a check of the lamp and alternator field circuit. When the engine is running and the alternator is working properly, the lamp is off. And when the engine is running but the alternator is not working properly, the lamp is on to warn the driver. The charge indicator lamp is connected between the ignition switch and the alternator field circuit. Battery voltage is present at the ignition switch through a connection at the starter solenoid. A resistance wire is connected across the lamp to keep the circuit operational if the lamp burns out, and the lamp circuit is completed through the alternator field to ground. When the ignition switch is on and the engine is not running, Current flows through the lamp and its parallel resistor to ground through the regulator and alternator field windings. This current is used to excite the alternator field. The current lights the indicator lamp. If the lamp is on with the ignition on but the engine not running, and it goes off with the engine running, this shows that the alternator is working. However, the voltage regulator can be out of adjustment and prevent a good alternator from properly charging the battery. The oil pressure indicator lamp is a similar warning device. When the ignition switch is on and the engine is not running, the lamp is on for a check of the lamp circuit. When the engine is running and the oil pressure is normal, the lamp will be off. And when the engine is running but the oil pressure is dangerously low, the lamp is on. This low oil pressure indicating system has an indicator lamp wired in series with a sending unit. The sending unit is tapped into the main oil gallery. It is electrically grounded and sensitive to oil pressure. There is an oil inlet on the sending unit, a flexible, pressure-sensitive diaphragm, and a set of spring-loaded contacts. The contacts are held closed until they are opened by the upward movement of the diaphragm. When the ignition switch is turned on and the engine is not running, battery current will flow through the switch, indicator lamp, and closed contacts to ground. The lamp will be on. When the engine is running, the oil pump circulates oil, building up pressure. About 5 psi of pressure is needed to push the diaphragm up and open the electrical contacts. This breaks the circuit for the indicator lamp. Current cannot flow, so the lamp will go off. It will remain off as long as the oil pressure is normal. If the oil pressure drops dangerously low when the engine is running, the diaphragm will move down and close the contacts. Current will flow and turn the lamp on. This would warn the driver that the engine and lubricating system should be checked at once to find the cause of low oil pressure. The third such on-off warning device is the temperature indicator lamp. When the engine is not running, the lamp will be on for a check of the bulb circuit when the ignition switch is in the start position, and will be off when the switch is in the on position. When the engine is running and the coolant temperature is okay, the lamp will be off. And if the coolant temperature rises too high, the lamp will turn on. This high temperature warning system has an indicator lamp wired in series with a sending unit. The sending unit is screwed into the engine. It is a simple make and break heat-sensitive switch. When the ignition switch is turned for cranking the engine, the lamp will go on even though the coolant is cold. A set of contacts in the ignition switch completes the lamp circuit to ground. The lamp will go off when the switch is turned to the on position. When the engine is running and the coolant temperature is cold or normal, the lamp ground circuit will be broken. Current cannot flow, so the lamp will be off. If the coolant temperature is high, as hot as 250 degrees Fahrenheit, a temperature-sensitive arm in the sending unit completes a circuit to ground. Current can then flow through the indicator lamp and switch to ground. The lamp goes on to warn the driver that the engine is overheating and should be stopped before serious damage results. Now let's learn how the various dash gauges work. You can easily understand gauge operation in 3 steps. We'll first study the basic meter movements, the operation of the gauge recording units, then the operation of various gauge sending units, and last, the applications of these units in typical gauge circuits. Gauge recording units are divided into 2 general types: direct reading and indirect reading. Voltmeters and ammeters are direct reading instruments. They record the actual charging voltage or current. Other gauges are indirect reading instruments, such as the fuel, oil pressure, and temperature gauges. They react only to changes called for by the gauge sending unit. The direct reading voltmeter and ammeter are very similar. They are based on a simple device called a galvanometer. This basic meter movement has a moving coil between the poles of a horseshoe magnet. A meter scale, balance spring, and scale pointer are other parts. The galvanometer depends on magnetic attraction and repulsion to work. Briefly, this is, like magnetic poles repel each other, and unlike magnetic poles attract each other. When a small current flows in the movable coil, the coil becomes a magnet with north and south poles. The magnetic forces between the coil and horseshoe magnet cause the coil to turn until the unlike poles are as close as possible. The coil stops turning when the magnetic force is balanced by the mechanical force of the spring. If the current in the moving coil is increased, the magnetic force is stronger. The coil can turn farther against the balance spring. This simple galvanometer has limited use. Very thin wire is used in the coil, and it can handle only very small currents and voltages. Thick wire, enough to handle battery current, is not practical. The meter would be huge. To measure high currents, a low-resistance shunt is connected in parallel with the galvanometer's movable coil. This makes a typical ammeter. Most of the current goes through the shunt, a small amount through the movable coil, and the meter scale is marked to tell the total current flowing through both paths. This type of ammeter is sometimes used to measure charging currents. Since its job would be to measure current flowing to or from the battery, the ammeter must be connected in series with the battery and alternator output terminal. The charging current has to pass through the dash connector twice, a disadvantage. To make a voltmeter for measuring voltage, a high resistance is connected in series with the galvanometer's movable coil. This resistance will limit the amount of current that can flow through the coil. The meter displays the voltage needed to push this small current through the coil. Unlike an ammeter, a voltmeter must be connected in parallel to the source of energy. Since it has a high resistance, it will not drain away current, which would reduce the voltage being measured. As a charge indicator, the voltmeter is connected in parallel with the battery, from the ignition switch to ground. This voltmeter reads the system voltage, and for convenience, a color-coded band is also used. Readings in the red areas indicate discharging or overcharging, while readings in the green area indicate charging. Indirect reading meter movements are just as easy to understand. There are three types of these movements. One is the ammeter used as an option on some AMC cars. It works like a conventional ammeter but has an external shunt, a calibrated length of 12-gauge wire between the battery and alternator. Whenever voltage is higher at the alternator end of the wire, the external shunt ammeter indicates charging. Whenever voltage is higher at the battery end, it indicates discharging. And when the voltage is the same at both ends, it reads 0. This type of charge indicator eliminates the disadvantage found with an ordinary ammeter. The charging current is measured in the battery to alternator circuit. It does not have to pass through the dash connector twice. In either case, an ammeter does not give a complete report of battery state of charge. The driver must judge the state of charge, since the ammeter shows only if the rate of charge is high or low. The voltmeter, however, shows the actual system voltage. The second type of indirect reading meter movement is the bimetal movement. It is used in gauges that operate with a constant applied voltage. These gauges are sensitive only to changes originating at the sending unit. A gauge with this type of movement has a bimetal unit attached to its needle. A heating coil is wrapped around the bimetal to provide heat. The bimetal expands and contracts as the heating coil changes temperature. The low voltage for a bimetal gauge comes from a constant voltage regulator, or CVR. Battery voltage is supplied to the CVR, which then supplies a steady voltage to the gauge. This prevents changes in battery voltage from affecting gauge readings. The CVR is built into some gauges, but more often one CVR serves several gauges. Here's how a gauge with a bimetal movement works. Current flows from the CVR through the gauge heating coil to the gauge sending unit, which is grounded. The sending unit controls changes in current flow. Depending on the amount of current, the heating coil provides heat to operate the gauge bimetal. The gauge needle moves as the bimetal changes size. If changes at the sending unit allow a higher current, the bimetal is heated and it expands, pushing the needle upscale. If changes reduce the current, the bimetal is allowed to cool and it contracts, pulling the needle downscale. The third type of indirect reading meter movement is called the balancing coil, or magnetic movement. This movement works off battery voltage and does not use a CVR. As with the bimetal gauges, it is sensitive only to changes at the sending unit. A gauge with this type of movement has two coils which have battery voltage applied to them when the ignition is on. One coil is grounded. Whenever current passes through the coils, they develop magnetic fields. The strengths of the magnetic fields control the gauge needle. If conditions at the sending unit allow a high current to flow through it, more current will flow through the right-hand coil. Its magnetic field will strengthen. The left-hand coil will have a weaker magnetic field. The gauge needle will be pulled upscale. If the sending unit allows very little current through it, the coils will produce balanced magnetic fields. The gauge needle will be pulled downscale. This magnetic meter movement depends on a variable resistance sending unit. The bimetal meter movement uses a similar type of sending unit. These sending units are not interchangeable. The indicator lamps use an on-off switch for their sending units. Depending on the gauge, the variable resistance sending unit reacts to changes in fuel level, oil pressure, or coolant temperature. When an engine condition or fuel level changes, the unit resistance changes. This controls the current flow in the gauge circuit. More resistance means less current. Less resistance means more current. The increase or decrease in current flow can be read by the gauge. Certain models of AMC cars and Jeep vehicles are equipped with bimetal type gauges. Others are equipped with the balancing coil or magnetic type gauges. Applications may change depending on the model year. However, you can readily identify a magnetic gauge from its instant response when the ignition is turned on. The bimetal gauge reacts slower because of the time needed to heat the bimetal. When the key is turned off, the bimetal gauge will return to low scale. The magnetic gauge will often stay where it is. Here's what the bimetal type fuel gauge looks like. It has a recording unit, a variable resistance sending unit in the fuel tank, appropriate wiring, and the CVR. As with all bimetal gauges, the recording unit has a heating coil wrapped around the bimetal. Current flows from the CVR through the heating coil and is grounded through the sending unit in the fuel tank. When the fuel level is low, the sending unit resistance is high. This holds current flow to a minimum. The heating coil provides little heat and the bimetal is contracted, pulling the gauge needle toward empty. When the fuel level is high, the sending unit resistance is low. This allows maximum current. The heating coil provides more heat and the bimetal is expanded, pushing the gauge needle toward full. The magnetic fuel gauge uses the same type of sending unit. The movement of a float up or down as the tank is filled or emptied causes a sliding contact to change the resistance of the sending unit. With high current through the sending unit, the right-hand coil will have a stronger magnetic field. It will pull the needle toward full. With low current through the sending unit, the coil magnetic fields will be balanced and will pull the needle toward empty. The bimetal oil pressure gauge is similar to the bimetal fuel gauge. The meter movements and operation are almost identical. The big difference is in the sending unit, where oil pressure changes operate a flexible diaphragm to increase and decrease resistance. The magnetic oil pressure gauge is similar to that for monitoring fuel supply, and its sending unit is similar to that used on the bimetal oil pressure gauge. The operation is no different than that for the fuel gauge. With low resistance, high current flows, and the right-hand coil will have a stronger magnetic field to pull the needle upscale. With high resistance, low current flows, and the coil magnetic fields will be balanced to pull the needle downscale. For the bimetal temperature gauge, the sending unit is a coil spring and sensing disc. Current passing through this coil encounters resistance based on the coolant temperature. Any change in resistance changes the current flow, and the gauge registers this change. The sending unit for the magnetic temperature gauge looks similar, but its resistance is different. It should not be used for a bimetal gauge application. The resistance of the sending unit is high when the coolant temperature is low. Low current flows, and the coil magnetic fields are balanced. This exerts a steady magnetic pull to hold the needle to the cold position. Then, as the coolant warms up, the resistance drops. Current increases through the right-hand coil as it decreases through the left-hand coil. When the temperature is high, the magnetic field of the right-hand coil becomes strong enough to pull the needle to the hot side of the gauge. All of these gauge circuits are in your film reference book for this training release, as are the highlights of other topics covered in this film. By using what you have learned here, the film reference book on diagnosis and service procedures will become a valuable aid in your work. These two training tools, plus your technical service manuals, should give you what you need to know about dash gauges and indicators.